quantum computers, they sound like something straight out of science fiction, right?
Yeah, totally.
Like, these machines could solve problems in seconds. Problems that take our regular computers, like, thousands of years. And guess what?
What?
Today's deep dive, it's all about a project that's using something pretty unexpected to build these crazy powerful machines.
Okay, I'm intrigued. What is it?
Diamonds.
Whoa, really?
Diamonds.
Yeah, we're diving deep into the world of something called the spinning project. And all thanks to this super cool article. It's from the Fraunhofer Institute. It's called Discover the Quantum Power Hidden Inside Diamonds.
Okay, that title alone has me hooked. Diamonds and quantum power. Sign me up.
Right. So get ready. Things are about to get pretty interesting.
I'm all ears.
So it feels like we're at this starting line, right, of a quantum race. And all these different teams, they're all trying to build the first, like, truly useful quantum computer.
Yeah, it's a pretty hot field right now. A lot of competition,
Yeah.
for sure.
Yeah.
And each team, they've got their own special approach. But spinning, with its diamond-based tech, they're definitely a serious contender.
Definitely. They're making some waves.
You might have heard about those superconducting quantum computers?
Yeah, they get a lot of press.
Right. They do. But this deep dive, we're going off the beaten path, you know.
Seems like it.
We're taking a look at this diamond-based approach.
So what's the deal with diamonds then? Why are they suddenly like the hot new thing in quantum computing?
Okay, so it turns out diamonds,
Ah.
they've got some hidden talents.
Oh. Like what?
So you see, spinning, they're creating these things called qubits. They're the building blocks of quantum information, right?
Yeah, the essential ingredient for a quantum computer.
Exactly. And they're making them using these like teeny tiny imperfections in a diamond structure.
Interesting. What kind of imperfections are we talking about?
They're called color centers.
Color centers. That sounds kind of artsy, not gonna lie. Not very high-tech.
I know, right? Sounds more like something you'd find in a painting class.
Exactly.
But hold on, because these color centers,
Okay.
they're the key to the whole thing. Picture them like tiny little traps for electrons.
Traps within the diamond.
Yeah, inside the diamond structure. And it's the spin of these trapped electrons. That's what we can use as a qubit.
Wow, so we're talking about harnessing like the weirdness of quantum mechanics
Uh-huh.
to turn these little flaws in a diamond into what? Like the engine of a new kind of computer?
Pretty much. It's kind of mind-blowing, right?
That's wild. But why go through all that trouble? What makes these diamond qubits better than other approaches?
All right, so that's where it gets really interesting.
Okay, wait on me.
See, one of the biggest problems with some types of qubits,
Yeah.
they're super sensitive to temperature.
Ah, I see. So they got to be kept incredibly cold.
Exactly. And that means you need those huge energy-guzzling cooling systems.
Makes sense.
But diamond qubits, they're way more stable at, like, normal temperatures.
Okay. So potentially diamond-based systems, they wouldn't need as much cooling.
Right.
That could be huge. Could revolutionize the size and cost of these things, right?
Totally. Like, imagine quantum computers moving out of these specialized labs and into more, like, everyday settings.
Yeah, that would be a game changer.
It would. And that's not all. Diamond qubits, they also have these longer coherence times.
Okay, coherence times. That means they can hold on to quantum information for longer, right?
Yeah, way longer.
And that's good because...
Well, think about it. Longer coherence times.
Yeah.
That's crucial for doing those super complicated calculations that quantum computers are supposed to be good at.
Right, like simulating molecules for drug discovery or optimizing crazy financial models.
Exactly. The longer a qubit can hold on to information without messing up.
The better your results.
Exactly. And the Fraunhofer Institute, they're saying their diamond qubits are less prone to those errors than other types.
Interesting. So less cooling, longer operation, fewer errors. This diamond approach is sounding more and more promising.
Right.
The article also mentioned something about working with 4 different types of color centers.
Oh, yeah.
What's the deal with that? Why so many?
Okay, so that's a great example of how spinning is, like, really pushing the limits.
Okay.
Each of those color centers, and they've got nitrogen vacancy, silicon and nitrogen, germanium, and tin.
Whoa, that's a mouthful.
I know, right?
So each one, it behaves a bit differently.
Yes, slightly differently. And that gives the researchers more options to fine-tune the qubits. You know?
I see. So it's like they're building a toolbox with all these different diamond-based qubits,
Right.
each one with its own, like, special skill set.
Totally. But before we get too carried away,
Yeah.
we got to talk about one of the most mind-bending things about quantum computing in general.
Oh, here we go. Lay it on me.
You ready for this? It's the thing that even Einstein called spooky action at a distance.
Entanglement.
You got it. Entanglement.
Classic. Every time I hear about quantum computing, entanglement's never too far behind.
Right. So, get this. The spinning team, they've managed to entangle 2 sets of 6 qubits each.
Okay, impressive. But over what distance?
Over a distance of 20 meters.
20 meters? That's like the length of a bowling alley. Seriously, that seems like a huge leap, way farther than I've heard about with other systems. What makes that such a big deal?
It's a massive step towards building bigger, more powerful quantum computers.
How so?
Well, you can think of entanglement as like the glue that holds these complicated systems together.
The glue. Okay, I like that analogy. So how does this diamond-based approach stack up against the more established technologies? The article mentions something about superconducting quantum computers using things called Josephson junctions.
Oh, yeah.
What are those exactly? And, how do they compare to Spinning's diamond tech?
All right, so Josephson junctions,
Yeah.
they're often shortened to SJJs.
Okay.
And right now, they're kind of the big players in the quantum computing world.
Right, because they've had tons of research and investment poured into them over the years.
Exactly. But here's the thing. Even though spinning system, it only has 12 qubits right now.
Uh-huh. That's a lot less than some of those SJJ systems, right?
Way less. Some of those have over 100.
Wow, so they're like the underdogs in terms of size.
Yeah, for sure. But they're still getting some pretty amazing results.
All right, I'm on the edge of my seat. Spill the beans. What kind of results are we talking about?
So first off, they're matching the error rates in single qubit operations.
Huh, really? That's impressive for a system with so few qubits.
Right. And remember those longer coherence times we talked
Oh,
about?
yeah. Those are important.
Well, we're talking milliseconds for Spinning's diamond qubits.
Milliseconds compared to what? Microseconds for SJJs.
Exactly. And over a much longer distance, too.
So even with fewer qubits, they're holding their own against the big guys in terms of accuracy and holding information for longer.
Yeah. This diamond approach, it's getting more and more interesting, isn't it?
Definitely. But I know nothing's perfect. What are some of the challenges the spinning field is still wrestling with?
Good question.
Well, one of the big things they're working on is improving the design of those resonator.
Resonators. Wait, remind me what those do again?
They're like these tiny little antennas,
Okay.
And they control and manipulate the qubits.
Ah,
You can think of them kind of like the conductor's baton,
Yeah.
orchestrating the whole dance of these quantum particles.
Right.
So to really squeeze the best performance out of the qubits, those resonators need to be super precise.
Got it. So they're like fine-tuning the tools
Yeah.
that let them control this whole quantum orchestra.
Exactly.
Cool. What about the software side of things?
Oh, yeah. So they're developing the software that manages the whole system,
Okay.
make sure it's running efficiently and all that.
Right.
After all, you're going to have a pretty sophisticated conductor to keep all those entangled qubits in harmony.
I like that analogy. So it sounds like they're tackling both the hardware and the software to make this diamond-based approach really work.
Yeah, they're going at it from all angles.
Cool. So what kind of real-world problems could these diamond-powered quantum computers actually solve?
Ooh, now that's where it gets really exciting.
I'm ready. Let's hear it.
Well, imagine using these machines to design totally new materials.
All right.
We could create super efficient solar cells that just soak up energy like you wouldn't believe, or develop these incredibly strong alloys that revolutionize construction.
Whoa. So it's like we're on the verge of a materials science renaissance, all thanks to these diamond-based quantum computers.
It's pretty mind-blowing when you think about it.
Totally. What about healthcare? Could they have an impact on medicine too?
Absolutely. Think about developing personalized medicine tailored to a person's specific genetic makeup.
Wow.
Or using quantum simulations to accelerate drug discovery, bring life-saving treatments to patients way faster.
Diamond-powered drug discovery. That's a headline I'd love to read.
Right.
What about AI? Could this totally change the field of artificial intelligence?
Yeah, there's a lot of talk about how quantum computers could supercharge AI.
Uh-huh.
They could make machine learning algorithms way faster, which could lead to all sorts of breakthroughs.
Like what?
Well, things like natural language processing, image recognition, and probably a whole bunch of stuff we haven't even thought of yet.
It's like opening a door to a whole new world of intelligent machines, all powered by the strangeness of quantum mechanics.
It's wild.
It is wild.
Yeah.
But it also makes you wonder about the cost.
Yeah.
Diamonds, even with imperfections, they're not exactly known for being cheap.
That's true.
So how does that factor into all of this?
Well, that's a good point. The cost of using diamonds is definitely something to consider. It'll be interesting to see how the economics of this technology play out as it develops further. Will it be a luxury technology or will it eventually become more accessible? Those are questions for down the line.
Right. It's a good reminder that scientific progress doesn't happen in isolation.
Yeah.
There are economic factors, manufacturing hurdles,
Yeah.
all sorts of real-world stuff to consider.
Absolutely.
Speaking of real-world implications, the article mentioned that this research is being funded by the German government.
Oh, wow.
What do you think that tells us?
Well, I think government funding like that shows they're taking quantum computing pretty seriously.
Yeah.
It's like a strategic investment in the future. Something with the potential to impact everything from national security to economic competitiveness. And it's not just Germany either. Lots of countries around the world are pouring money into this field.
So it's not just a scientific race. It's kind of a geopolitical one, too.
Yeah, you could say that whoever figures out quantum computing first could have a huge advantage in a lot of different areas.
It's like we're watching a race to harness the power of quantum mechanics to solve the world's toughest problem.
Exactly.
This is fascinating stuff. Before we wrap things up,
Yeah.
I'm curious, what stood out to you the most about this whole diamond approach? Anything that particularly surprised you?
Honestly, it's the fact that they're getting these results with such a small number of qubits.
Yeah.
Like, they're matching the performance of these much larger superconducting systems. That's pretty remarkable. It suggests this tech has some serious potential for scaling up.
It's like they're proving you don't need the biggest system to make huge advancements.
Right. It's about quality, not just quantity.
I'm also really interested in their focus on entanglement over those long distances.
Yeah, that 20-meter entanglement thing is a game changer. It opens up so many possibilities for the future.
That they're not just taking small steps, they're making these giant leaps forward.
Definitely.
Okay, so we've covered a ton of ground here. Our listeners practically an expert on diamond-based quantum computing now.
Well, maybe not an expert, but they've definitely got a good grasp of the basics and what makes this approach so unique.
Before we go, I want to leave our listener with one final thought to ponder.
Okay, shoot.
We've talked about the technical stuff, the potential applications, but what about the bigger picture? As these technologies keep advancing, what kind of impact are they going to have on society as a whole?
That's a really important question. With any powerful technology, there are always societal implications to consider.
It's not just about the science itself. It's about how we use it and what kind of future we create with it.
Absolutely. It really does feel like we're standing on the edge of this whole new frontier. It's pretty amazing to think about all the possibilities and the challenges, too.
It's a good reminder that scientific progress, it's not just about the formulas and lab experiments. It's about how those discoveries actually change the world, change our lives.
For sure.
But before we get too deep into the philosophy of it all,
Okay.
let's bring it back to diamonds for a sec.
All right.
We've talked about how they could be used in quantum computing. But what about, the ethics of it all?
Ah, interesting.
Are there any concerns about using diamonds this way?
That's a really thoughtful question. When we talk about ethics, the focus is usually on how the technology is actually used, not the materials themselves.
Okay, see.
So the real ethical questions come up when we think about what people might do with quantum computing,
Right.
Like, how can we make sure this incredible power is used for good and not to make existing problems worse?
It's like we're not just building a new gadget. We're shaping the future. And that comes with some serious responsibility.
Exactly. We have to talk openly and honestly about what quantum computing could mean for the world.
To make sure it benefits everybody. Well said.
So,
So, to our listener, you've just gotten this, sneak peek into the cutting edge of quantum computing.
the world of diamond-powered computers.
Who would have thought those sparkly gems held the key to such mind-blowing technology, right?
It's amazing, isn't it? Diamonds. From, crowns and jewelry to...
Quantum computers.
Exactly. Talk about versatile.
This diamond-based approach, it's still early days, but the progress they're making is super exciting. Less cooling, longer operation, fewer errors, entanglement over long distances. It's a pretty powerful combination.
And who knows what other breakthroughs are waiting just around the corner. It's really inspiring, It shows what humans can achieve when we push the limits of what's possible.
So next time you're feeling uninspired, just remember those tiny imperfections in a diamond, those color setters.
Yeah.
They're being used to create machines that could change everything. Sometimes the most unexpected things have the biggest potential.
Couldn't agree more. It's a good reminder to stay curious, to keep exploring, and to never underestimate what science can uncover.
Well said. Thanks for joining us on this deep dive into the fascinating world of diamond-based quantum computing. We'll catch you next time for another deep dive into the frontiers of knowledge.